Again, welcome to Mathematical Structure for Computer Science. This is CS 113, also known as Discrete Mathematics at Pace University. So in these lectures, we're going to continue with our set topic. In the previous lectures, we discussed about the definitions of a set and some of the set properties. In these lectures, we're going to cover the set operations. So our main objective is to go through the set operations: union, intersection, complementation, and difference. Then we also go through the set cardinality. In our previous lecture, we discussed or defined what cardinality means. Again, a set cardinality means the number of elements the set has. It's called a set cardinality. We're also going to discuss about set identities and how to prove the identities. And our last option, objective, will be membership tables. So here we say the set concept is almost same as Boolean algebra when we talk about the set operations. So here we say propositional calculus and set theory are both instances of an algebraic system called a Boolean algebra. This will be discussed in chapter 12 or unit 12 of our lectures. Now, the operators in a set theory are analogs to the corresponding operators in propositional calculus. As always, there must be a universal set. And as we discussed in our previous lectures, a universal set is a set that have all the elements. So, example, a universal set of English alphabetical letters would be 26. That's from A to Z. All the letters from A to Z will be a universal set for English alphabetical letters. So let's start with the set operations. And here we start with the union. A union means if I have two sets, let's say example, A union B, it means all the elements in set A or all the elements in set B. So the definition said, if we have two sets, A and B, the union of the two sets will be all the elements in A or all the elements in B. So example, I have, let's say set A is 1, 2, 3, and set B is 3, 4, 5. The union of A and B will be 1, 2, 3, 4, and 5. And there's no need of duplicates. There's no duplicates. So here we can see the solution is 1, 2, 3, 4, 5. So set A union B, all the elements in A or all the elements in B, no duplicates. Then intersection means we only need the element that is in both A and B. Only elements that is in both A and B. So here we say in the intersection of set A and B denoted as A intersect B is, we can see the term here, is every S represent the element. So every element that belongs to A and also that same element that belongs to B. So union was all the elements in A or all the elements in B. So we need all the element don't have to be in both A and B. It have to be only, it can be in both A and B. We don't take a duplicate. Then it can be in only A and only B for union. By intersection, we only need the element that is in both A and B. So we say AND. We use again AND operator. So we can even see from the Venn diagram. We have set A, set B. We can see the shaded area is the element in both set A and B. So a good example, we are using the same example as our union of A and B will be 1, 2, 3, 4, and 5. In the previous example, we said, let's assume set A have elements 1, 2, 3. Set B have elements 3, 4, 5. So A union B will be 1, 2, 3, 4, 5. Now, A intersect B will be only 3 because 1, 2 is not in set B. and also 4, 5 is not in set A. So intersection of a set with element 1, 2, 3 and 3, 4, 5, the answer will be 3 because 3 is common in both. So we can see the solution is 3. Now here we have 1, 2, 3, 4, 5, 6. Intersection of 1, 2, 3, 4, 5, 6 will be 0, empty, nothing. So we have no, because there's no any element that is common in both sets. Now if it's union, then it will be 1, 2, 3, 4, 5, 6. Because union is every element in A or every element in B. But intersection is every element in A and is also in B. So only the element that is in both sets is intersection. So let's go to the third operation, which is complement. If we quite remember in unit 1, when we are doing propositional logic, we talk about complement, negation. So for example, in Boolean algebra, the complement of true is false. The complement of false is true. Now we use the same concept here. So we can even see from the Venn diagram. If I have A items A complement means that items is not in A or the elements. So if I have, let's say for example, I have set A, the elements are 1, 2, 3. The complement of it will be any items except 1, 2, 3. So we can see the definition. If A is a set, then the complement of A with respect to the universal set donated by A bar, so a complement of A is A bar, is the set of U universal set minus, again, set A elements. So that's why we said the complement of A is every element that is not in set A. So we can see that we are subtracting all the elements in A from the universal set. And we can see the expression here. If S element belongs to universal set, then the complement of A is all the element that is not in A or doesn't belong to A or is not a member of A. So again, A complement is element that is not in A. So for example, if universal set is the positive integers less than 100, what is the complement of S greater than 70? So we know all the elements are less than 100. We go up to 99. Now we say what is the complement of all the element that is greater than 70. So they have to be, if it's greater than 70, then it's less than 70 complement. A complement of true, opposite of true is false. The complement of A means every element that is not in A. I mean, every element that is in A is not in the complement of it. So the answer here, since we said S is greater than 70, and we are looking for the complement of elements that are greater than 70, then the answer will be all the elements that are less or equal to 70. So the solution will be S is less than or equal to 70. So complement is like opposite. Complement of B means all the elements that are not in B. Then our last operation is the difference. So in this, again, we're going to continue with set in our next lectures. In these lectures, we are learning 4 main operations, the most common ones used: union, intersection, complement, and difference. So difference is, example, if we have a set A and B, the difference of A and B donated by A minus B is the set containing the element of A that are not in B. So the difference of A and B is also called the complement of B. So if we understand the concept of complement, because we said, okay, here I'm subtracting B from A. So the answer that I will get means there's no B element inside. So the difference of A minus B will be the complement of B. Or the difference of B minus A will be the complement of A. Because the answer will be all the elements, but that doesn't have A inside. So it's the complement of A. So again, if I have A minus B, it means we need all the element that is in A and also the element that is not in B. So this is the same as writing A intersect B complement. And also we can say the answer will be B because again, we want all the element that is in A, but it's not in B. So A minus B is like a complement of B, but with respect to A, not with respect to universal set. When we talk about complement, we always make it in respect to, again, universal set. But A minus B means A is everything that is in A, but it's not in B. So it will be complement of B with respect to A. So again, we finish with the four operators. We say union means, let's say if we have a two set, the union of two set means all the elements in set A or all the elements in set B. Intersection means all the element that is in A and also is in B, so the common. And also we talk about complement. Complement is with respect to the universal set. So complement of A means all the elements that is not in A. It will be the complement of A. Complement of B means all the element that is not in B. Then the last one we talk about difference. A minus B means all the element that is in A but it's not in B. So it's at the complement of B with respect to A. So we move on to the cardinality of the union of two sets. So we talk about the cardinality means the number of elements in each cell. So if in each set, so if I have a set A and I have 10 items, then the cardinality is 10. But also here we have a union. A union means we are combining two or more sets together. So what is the cardinality of a union of two sets? We can see that we did probability. We saw this concept in probability special addition rule or it's called the general rule. So you can see that A union B means all the element in A plus all the element in B minus the element that is in both A and B, which means we want to remove the duplicate. We are not going to count the duplicate. So because cardinality is the number of elements in a cell, in a set. So if I'm trying to find out how many elements in a set of A union B, then I'll count all the element that is in A, all the element that is in B. Then if there's any element that is in both A and B, I'll subtract that element 1 from it. So this is example. Here we say let A be the math majors in your class. So let's set A be the math majors in your class and B be the computer science majors. To count the number of students who are either math majors or computer science majors, add the number of math majors and the number of computer science majors. And then you are going to subtract the number of joint if we have students that is taking both computer science and math majors. And again, we will return to these principles in chapter 6 and 8. And that will be our unit 6 and 8 lectures, where we will derive a formula for the cardinality of the unions of n sets, where n is again a positive integer. But the only thing we should know first in our previous set We know cardinality means the number of elements in a set. Now, if I have only one set, it's easy, just count them. And the number of elements, no duplicate. But if I have A union B, then I'll count everything in A, I'll count everything in B. Then I'll subtract with how many items are duplicate. That it means how many items that are in both A and B. We subtract. So let's say review some questions here. And these questions will cover most of the set operations we went through now. So we have a universal set from 0 to 10. We have set A is 1, 2, 3, 4, 5. Set B is 4, 5, 6, 7, 8. First, we want to look for the union of set A and B. So the union of set A and B will be 1, 2, 3, 4, 5, 6, 7, 8. 4 and 5 is duplicate, so we subtract it. So we get our answer to be 1, 2, 3, 4, 5, 6, 7, 8. Because the union again means all the elements in A and also all the elements in B, excluding the duplicates. We don't need duplicates. Duplicate means we have the same element in both sets. Now the intersection, I've say 1, 2, 3, 4, 5, and here I see 4, 5, 6, 7, 8. Intersection means the elements that are in both sets. So I can say that in set A, I have 4, 5. In set B, I also have 4, 5. So our answer will be 4, 5. Then the next will be the complement of A. Remember the complement of A is with respect to the universal set. So I'll go to the set A and I'll look all the elements that are there. And I'll make sure I'll go to the universal set and I'll make sure all the element that is in A, I'll remove all of them. And the rest of the elements that is in universal set will be my complement of A. So I have 1, 2, 3, 4, 5. So the complement of A will be 0, 6, 7, 8, 9, 10. So let's see the answer. So 0, 6, 7, 8, 9, 10. Because the complement of A means all the element that is in a universal set, but it's not in set A. It's not in set A. So complement of B also will be the same concept. I'll go to B. I have 4, 5, 6, 7, 8. So I'm going to remove all these elements in B from universal set. Then the rest will be our complement of B. So the answer will be 0, 1, 2, 3, then 9 and 10. So 0, 1, 2, 3, then 9 and 10. These are the elements that are not in set B. So that have to be the complement of B. Now, A minus B, as we said earlier, means the complement of B, but with respect to A, not with universal. So I'll go to A and I see 1, 2, 3, 4, 5. I'll go to B, I see 4, 5, 6, 7, 8. So I'm going to subtract B from A. So in this case, 4, 5 is here. So we remove 4, 5. So our answer will be 1, 2, 3. So A minus B, again, is like a complement of B with respect to A. So I'm looking for all the element that is in A, but they are not in B, and it's only 1, 2, 3. The same thing will go opposite. B minus A means I'm looking for, that's the complement of A with respect to B. So I'm looking for all the element that is in B, but it's not in A. So B, we have 6, 7, 8. So the answer will be 6, 7, 8. So I hope these examples again make us understand all the operations we went through now, the set operations. Again, the union, intersect, complement, and difference. 5 operations. So next we go to the symmetric difference. In our course textbook, we say this is an optional topic. So the symmetric difference, it has a symbol cross with circle around it. So a symmetric difference of A and B denoted by A symmetric difference B is the set A minus B union B minus A. So we can see again symmetric difference. We are looking for all the element that is in A and also is in B, but it's not in both. So I start with A, symmetric difference B. It will be find the complement of B with respect to A, then the complement of A with respect to B, then union both of them. So that's why we are getting this area and we don't get the comma. So the answer here will give us A minus B will give us, we have 4. So we take 4 and 5, so it will give us 1, 2, 3. Then B minus A will give us 6, 7, 8. So the answer will be 1, 2, 3, 6, 7, 8. So 1, 2, 3, 6, 7, 8. Because we find A symmetric difference B means complement of B with respect to A, union complement of A with respect to B. So next we move to the set identities. Remember again in Boolean algebra, we talk about Boolean identities. The concept is the same. We can use these identities to solve set operations or set problems. So the identity loss, we say A union 0 or null, the answer will be A. Also A intersect universal, the answer will be A. What we're trying to say here is that if I have a set A and I union it with empty set, then empty set, there's nothing in that set. So the answer will be A. Or if I have set A and I want to intersect it with U, what will be common, since universal set have everything, whatever is in A also is in universal set. So the answer will be A. Domination rules, we said A union universal, the answer again, because we talk about no duplicates. So everything that is in set A is in universal set. So A union universal set, the answer will be the universal set. And also A intersect empty set, the answer will be empty set, because empty set, there's nothing inside. So that means the two sets doesn't have anything common. So the answer will be no or empty set. Then we also know that A union A, the answer will be A, because we have the same element in A, the same element in A, second A. So the answer will be the same element, no duplicate. Same thing with the A intersect A, we have the same element in both. So the answer will be A. Complement, if you have two complement, they will cancel each other. So A complement will be A. Actually, we use this rule also in Boolean algebra. Then we have the commutative loss. A union B is the same as B union A, or A intersect B is the same as B intersect A. This is commutative loss, arithmetic operation too. Associative loss, A union parenthesis B union C is the same as A union B parenthesis, then U, and then union C. Or A intersect parenthesis B intersect C is the same as saying parenthesis A intersect B, then close parenthesis, then intersect C. So the position of the set doesn't matter. Then the distributive loss, this is where we have a little bit different from our arithmetic operation. So if I have A intersect B union C, B union C is in a parenthesis. So we are going to multiply A intersect B, then the union, then A intersect C. So it will be A intersect B, union, then A intersect C. The same thing applies to A union B intersect C. So we multiply A union B intersect A union C. So A union B intersect A union C. And also we use the DeMorgan Loss in Boolean algebra, the same rules. So DeMorgan Law said if we intersect, complement everything, the intercept of union, the complement of union is intercept. The intercept of union, the complement of union is intercept, and the complement of intercept is union. And that's what I want to say. Again, the complement of union is intercept, and also the complement of intercept is union. So this is the same as Boolean algebra. The complement of plus, we have it minus or multiplication, n is or is n, and the same concept here. So if I have A union B or complement, if I want to separate it, then I'll get A complement intercept B complement. So A complement intercept B complement. The same thing if I have A intercept B or complement. If I want to separate it, then I'll get A complement, intercept complement become union, then B complement. In absorption rule, same as Boolean algebra, A union, A intercept B will give me A. Then A intercept A union B will also give me A. Then complement loss, if I have A union A complement, is universal. If I have A intercept A complement, is empty, no. So proving set identities, again, there are different ways to prove all these set identities, and we did that already in Boolean algebra. Also, we can prove the identities. Here we prove that each set inside that is side of the identity is a subset of the other. So we can prove that each set, which is the side of the identity, is a subset of each other. So we can use the set builder notation and also propositional logic. Then the membership tables that verify that elements in the same combination of sets always either belong or do not belong to the same side of the identity. We can use 1 to indicate it is in the set, or 0 to indicate that is not in. So let's see some example here. Here they say we should prove of second DeMorgan law. And this is second DeMorgan law, said that A intercept B or complement is the same as A complement union B complement. So we prove this identity and show that A intercept B complement is a subset of A complement union B complement. And also A complement union B complement is a subset of A intercept B or complement. So we start with the steps here. So we want to prove that, again, A intercept B complement is a subset of A complement union B complement. So first, we know the absorption law. By absorption law, we can have the element belongs to A intercept B or complement. Then with the complement means S that doesn't belong to A intercept B. So S belongs to, if S belongs to, S element belongs to A intercept B complement, then S element doesn't belong to A intercept B. So here we can say, okay, if S belongs to A and S belongs to B, then not S belongs to A or not S belongs to B. And then we have S not belongs to A or S not belongs to B. Then we have S belongs to A invert or S belongs to B invert, which is complement. Then S belongs to A complement or invert, union B invert. So this is the steps we are proving that A intercept B complement is the same as A complement union B complement. Because if we know that the element belongs to A intercept B or complement, then the element doesn't belong to A intercept B. We know the complement. And we can write this by using intersection, saying that not, again, this is complement negate. So not S belongs to A and not S belongs to B, which is from our second. Then we say not S belongs to A or not S belongs to B. We open the parentheses. Not S belongs to A and S belongs to B. So we make it separately. Then we know that S not belongs to A and S don't belongs to B. Based on this, not S belongs to A, not S belongs to B. We already changed the intersection because we use the negate for every. This section is the same as writing it in this form. Then we break it into two. So we negate everything inside. So we change negation of N to, again, or. And actually, when we reach here, we finish our proof. Because all we have to see, if not this, then S don't belongs to A and doesn't belongs to B. So we have, if it doesn't belongs to A, then it will be A invert. If it doesn't belong to B, then it will be B invert. So we get A invert union B invert. So union is the same as or. So again, propositional logic in chapter 1 or unit 1, this symbol represents or disjoint. And this symbol represents N. N is like multiplication and product. And so this is a second example. We have A invert, union B invert is a subset of A intercept B or invert, or be the same too. So we start with the A invert union B invert. We know S belongs to A invert or S belongs to B invert, union or. And this means S doesn't belong to A. If S belongs to A invert, means S doesn't belong to A. The same thing apply here. We have B invert, so S doesn't belong to B. If we say doesn't belong, then it's negation. So we put negate S belongs to A, then S doesn't belong to B. Negate S doesn't belong to B. So to remove the negation, we are going to change the N to or. And N to or will, we are going to change or to N. Again, N is the V opposite. This is N. V is or. So when we negate everything here, we are going to negate the or and change to N. N is the same as intersection. So here we can see that we negate everything, A intercept B. So we have what we call the set builder notation, which is the second DeMorgan law. We have A intercept B or invert is the same as saying that X doesn't belong to both A intercept B. It doesn't belong because A intercept B invert means A intercept B means what is in A and what is in B. Invert means what is not in both of them. So it's same writing the element S doesn't belong to A intercept B. Then we can change not belongs to invert. Then we say S belongs to A intercept B. This section and the next line is the same. Instead of saying not belong, we say belong, but invert the belong. Then we move to the next. We have A intercept B. We can write it as A and S belongs to B because we just said that Intersection means everything that is in A and everything that is in B. So we break it down here using the N. Everything in A and everything in B is the same as A intersect B. Then this will take us to the next line. We separate the two. Not S belongs to A. Again, negation will apply to this. So now this time N will change to O. So not S belongs to B. And after that, we almost finished. So here we remove the negate. We say not belongs. We remove negate, not belongs. So not belongs means it's invert. Belongs invert, belongs invert. And we already changed the sign from, again, O to, from N to O. Again, V is O. And opposite V is again N. So again, this is a proving that A intersect B or invert is the same as A invert union B invert. So this is what we call the membership table. Sometimes we can use the membership table to do what we call our proving. More or less in Boolean algebra, it's like the truth table, So we can construct a membership table to show that the distributive law holds. So here we have A union B intersect C is the same as A union B intersect A union C. So in Boolean algebra, we will call this table a truth table. So if both A union B intersect C have the same 0, 1, 0, 1 with A intersect B, A union B intersect A union C. If both of them have the same 0, 1, 0, 1s, then we prove that they are the same. And in this case, we can see, so first we start with count how many variables we have here, or how many letters we have. We have ABC. So this means we are going to have 8 possible combinations from 111 or 000 to 111, 2 to the power 3. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 possible combinations. So we start with 000, 001, 010, 011, 100, 101, 110, then 111. Then first I know I have B intersect C. So I will put B intersect C, 1, 1 is 1. And remember, intersect is multiplication. Union is addition. So BC is 1, 1, then B intersect C will be 1. B is 1, C is 0, so 1 times 0 is 0. 0, 1 will be 0, 0, 0 will be 0. We only get 1 when both are 1, 1 for intersect. Now we go to the union. You see the union is addition. So if one of them is 1 or both of them is 1, we get 1. So the only time we get 0, 2 zeros here is when A and B are 0, 0. So 0, 0, 0, 0. So again, membership table is the same as truth table. But in Boolean algebra, we use the term truth table. In set, we use the term membership table. So after we find the A union B, we're also going to find A union C. Remember, it's addition also. So look at AC, 1, 1, 1, 0, they are 1, 1. 1 plus 1 is 1, 1 plus 0 is 1. The only time we get 0 is this section because we have A is 0, C is 0. And the last one, A is 0, C is 0. So 0 plus 0 is 0. Apart from that, everything is 1. And when you are doing multiplication, which is intersect, right here, we only get 1 if both of them are 1. If it's 1, 0, 0, if it's 0, 0, 0. So now we know B intersects C. So we have union here now. B intersects C plus A, and that will give us the answer here. So we get 1. Since every A is 1 throughout, is 1. Next we have A is 0, but B intersects C is 1, so it's 1. Again, we have A union is plus. So we get the values. Then to get A union B and A union C, we have them here already. So we just intercept them. We only get 0 if one of them is 0. So here everything is 1, 1, 1, 1. So here 1 times 0 is 0, 0 times 0, 0 times 0 is 0. So we can see that A union B intersect C It's the same values here as A union B intersect A union C, the same value. So this is using the same idea of a truth table in Boolean algebra. But remember again, union is plus, intercept is multiplication, or the or and n is multiplication, or is plus, to construct the membership table. Again, one more time. First thing you do, count how many variables you have, or how many letters, A, B, C. If I have A, B, C, D, then I'll get 16 combination A, B, C, D from 0, 0, 0, 0 to 1, 1, 1, 1. Here we have 3, so we go from 0, 0, 0 to 1, 1, 1, 1. Or you can start from 1, 1, 1, 1, highest to the lowest, or lowest to highest, the same. Then we apply, I have B intercept C, so I need to find it. Intercept against multiplication. Then I have A union B, so we have that one. I also have A union C, we find that also. Union means addition, so I'll add A plus B, next time A plus C, up to all the possible 8 rows. Then we find A union B intersect C, and also A union B intersect A union C. Then if the outcome is the same, then we say we prove it. This is the most quickest way or easy way to prove if two set operation here or set expression here are the same. So we have what we call the generalized unions and intersections. So here we select A1, A2 up to A and B, an index collection of sets. So we can define the universal from 1 to n. A1, that is from A1 union A2 all the way to union AN. Intercept also the same from 1 to n. We can have A1 intercept A2 up to AN. N is the number of elements in the set. So we have the union and also the intercept. So these are well defined since union and intercept are associative. And this will take us to the conclusion of our lecture. So in these lectures, again, we learn about the set operations. The set identities, as I said earlier, are the same as Boolean algebra, which we already covered. And then how to prove if two expressions are the same, we use what we call the membership table. Is the same concept also in Boolean algebra, which we call the truth table. Remember, intersection is multiplication. Union is always addition when we are doing your expressions. So again, wish everybody the best and see you in the next lectures. Thank you for your time.